In our next example on energy conservation, we have something that looks very similar to the previous video. We have a block sliding up a hill, given some initial velocity. This block has a mass of 5 kilograms. The angle is 30 degrees. The question is, how far will it go up the incline before it comes to a complete stop? But there's friction in this case. There's a coefficient of friction of 0.2. So how do you do a problem like that? The concept is no different. We can say that the energy initial equals energy final, which means that any work put into the system plus any initial potential energy that it has plus any initial kinetic energy that it has must equal the final state, which means any final potential energy that it has plus any final kinetic energy that it has plus any heat lost or energy lost due to friction. So any energy lost. All right, so that's always the case. We always use that very same equation. Now we have to determine which of these terms are not needed. Well, for one thing, there's not a continual push up the incline, so no work put into the system. That goes to 0. We can arbitrarily choose this to be the 0 height start. So that means that there's no initial potential energy in the system. And by the time the object reaches this height right here, V final is going to be equal to 0, so that term is 0 as well. So kinetic energy final goes to 0. So we have initial kinetic energy because it has motion. It will have final potential energy because it will have gained height. So there's going to be an increase in the height. And then there's going to be energy lost because there's friction. And so we have to take that into account. Now they're not asking how high the object will go, they're asking for how far the object will go up the incline. So we have to relate h to d, and I don't have to write delta h, I can simply just say h, and we can then say that the definition of the sine of theta is equal to the ratio of the opposite side over the hypotenuse. And since we're looking for the hypotenuse d, we can say the hypotenuse is equal to the opposite side over the sine of theta. In other words, we could say that the hypotenuse, which is d, is equal to the opposite side, which is h, divided by the sine of theta like that. So, or, since we're going to figure out what h is equal to, we could say that h is equal to d sine theta. All right, knowing that, let's plug in what we know. It has initial kinetic energy because it's moving. So we could say that it has 1/2 mv initial squared. That equals the final potential energy, which is going to be the final mgh. So mgh final plus the energy that's lost by overcoming friction, which is the force times the friction force, because you have to push with an equal but opposite direction of the force. The friction force, so the friction force is this way. You're going to have to push against the object with an equal and opposite force. Of course, we're not actually pushing the object with a force. So where's that coming from? How can that happen? Because you're not physically pushing it. Well, to overcome the friction, you're simply taking the energy out of this object to the amount necessary, as if you were pushing the block up the hill with the force equal to the force friction. So what that means then is, we're going to, right here, force friction times the distance that we cover. That's going to be the energy lost. So we have to figure out what the force friction is. And we have to convert from h to d using that equation right there. So how much friction or how much force is the friction pushing down with? Well, we have the mg, the weight of the object. We have the mg cosine theta term, mg times the cosine of theta, which is the perpendicular component of the weight. And then, of course, we have the mg sine of theta that's parallel to the incline. Then, of course, we have the normal force, which is the incline pushing back on the object. That's the normal force, and that's going to be equal in magnitude to the mg cosine of theta. And finally, we then know that the friction force, by definition, force friction, which is equal to the normal force times mu, and since the normal force is equal to this, we can say that it's equal to mg cosine theta times mu. So then, plugging all that into our equation here, we can say that 1/2 mv initial squared is equal to mg, and instead of h final, we're going to write it as d sine theta. So we'll write this as d sine theta plus the friction force, which is going to be mg cosine theta times mu, mg cosine theta times mu, and the whole thing multiplied times d. Now, notice, we know the mass, but we don't really need the mass because every term has an m in it, so the m's cancel out. So we don't have to worry about the m over here. Notice we do know the initial velocity, that's given. We know g, d is what we're looking for. We know the angle theta. G is known, we know the angle theta, we know mu, and we look for d. So the only variable left in there that is not known is the variable d, the displacement or the distance traveled by the object. And now we have to algebraically solve this equation for d. So the best way to do that is to factor out the d and then divide both sides by what's left. So we have 1/2 v initial squared is equal to g sine theta plus g cosine theta mu, and the whole thing multiplied times d. So what I'm doing here on the right side is factoring out the d. Then I divide both sides by this quantity, flip the equation around, so now I can say that the distance traveled is equal to 1/2 v initial squared, which is the left side equation, divided by this whole thing right here, so divided by, and of course notice I can factor out a g, so divided by g times the sine of theta plus the cosine of theta times mu. And that will tell me how far the object will move along the incline before coming to a complete stop. And it's this portion right here of the equation which takes into account that we have to overcome the friction. So let's plug in all the numbers that we know. The initial velocity is known, and I'm going to leave out the units to make it a little bit cleaner of an equation. It's 1/2 times 20 squared divided by 9.8 times the sine of 30 degrees plus the cosine of 30 degrees times mu, which is 0.2. And now with a calculator, we can figure out what that is equal to. So we take 30, take the cosine of that, times 0.2, add to that the sine of 30, that's plus 0.5, then multiply times 9.8, which is the denominator, take the inverse of that, put it into the numerator, times 0.5, and then times 20 squared, which is times 400, equals, and that gives us 30.3 meters. So this is equal to 30.3 meters. That's the distance that the object will travel up the incline. And so keeping in mind is that all it had initially was some kinetic energy due to its velocity. That kinetic energy was used to increase its height, therefore traveling a distance up the incline, plus also overcoming the friction along the way. So based upon that, it made a distance of 30.3 meters. If it wasn't for the friction, it probably would have made it quite a bit farther. But again, start out with the basic equation, figure out what's not there, what's equal to 0. You're left with the 3 terms right there. Plug in the equations for each of those 3, and then solve for the unknown variable. And that's how you do a problem like that.